Hello. Standard diffusion is often in disagreement with quantum predictions, for example, for electron conductance, also for neutrons, protons. For example, for 0-1 infinite potential well, standard diffusion predicts stationary probability distribution as uniform, while for quantum mechanics, it is sign squared. It's completely different. Here are some examples for electrons in semiconductor from scanning tunneling microscope. And we talk about introduced to random walk, maximal entropy random walk, which repairs this problem by using random walk, which maximizes entropy production as it should be done for statistical physics models, and show it about show examples for new articles about the PN junction, that we will model this PN junction, and literally if attaching potential in one direction, there will be electron flow, diffusion in the opposite, there will be no. So let us briefly look at some simple simulator. So here is a lattice of lattice, homogeneous lattice with some defects. So the line means that the edge is removed. So some edges are removed. And here is for standard random walk. Standard random walk, removed edge means that the probability is so the stationary probability is proportional to the degree of vertex. So we can see that it's reduced only for these lower degree vertices, while for maximal entropy random walk, the stationary probability distribution shown is exactly different. Yeah, so we can see it's much stronger localization. So we can see now what is the dynamics. So for maximal entropy random walk, it will indeed go to this ground state. While for switching from generic random walk, it will go to nearly uniform distribution. It's completely different behavior. You can also for conductance attach this potential difference. So now they should flow, and this standard random walk. And now for MERW. So we can see again completely different behavior. Now the flow localizes in this least resistance path, like kind of some short circuit. Okay, let's go back to the talk. Okay, so we have two basic philosophies of getting probabilities for a single walker. Yes, so the standard picture is the stochastic picture, that we assume some stochastic propagator, literally assuming that if there is a drunken sailor, he sees 6 possibilities, he throw a dice and choose according to this assumed uniform probability distribution. So the question is, can we assume? Do we know it? So how to choose it? From the opposite direction, there is ergodic picture that assumes that we have some deterministic evolution, that we know the deterministic propagator, and it averages to some probability distribution. But so both assume that we know something. Yes, the stochastic propagator, how the object behaves randomly, or an ergodic that we assume the deterministic behavior. So maybe we don't have this knowledge. So maybe we should be less certain. So I propose this central, this thermodynamical picture, so statistical physics picture, that if we know that the walker is in given position, to get his next position, so we should assume ensemble of potential paths he travels, and from this ensemble uniform without potential, finally Boltzmann, we get the probability of the next step. Yes, so we get the propagator from the paths ensemble. Yes, so this model is non-local. So to get the formulas, we really have to know the entire space. However, this is effective model. Only we are supposed to use it, not the walker. So the walker has some complex hidden behavior. This is just model used by us to have his most likely behavior. So this is based on this James Maximal principle I mean, to talk further about. Okay, so here is some overview of various situations. So once again, for 0-1 range, infinite potential where standard diffusion says 0, uniform distribution. For quantum mechanics, the sine square. Assuming paths from now toward future, uniform the ensemble of paths, then you get the first power. That's just sine. Assuming from now toward paths, path ensemble, you get again first power. But to get sine square, we have to use ensemble of full paths from minus infinity to plus infinity, just crossing it in current time. So literally to get some given value, we have to randomly get it both from the past and future half ensemble. So indeed we get that the Born rule from the time symmetry that we have. Yes, so from asking about probability distribution at the end of time or Ising model, it's very similar to Ising model using Boltzmann path ensembles. We also get we get the first power, but in the center we get second power because of meeting of past and future half paths. So here is for the electrons from tunneling microscope. Here is for neutron. The bottom right is for neutrons. So the solid line is for the classical behavior. The dotted line is the quantum ground state, and we can see that experimentally it indeed was the ground state. So again, like this sign square instead of uniform for electron. But also they get it for some solitons for bouncing droplets. They are this very nice experiment that they have this vibrating surface of fluid, and there is droplet bouncing, and looking at trajectory, they can get quantum-like statistics for them. So it is not only for microscopic objects, but maybe for macroscopic, like these bouncing droplets. Okay, so what is this James maximal entropy principle? So for example, having some sequence of n zeros and one, the question is what percentage of one should we assume if not knowing anything? So intuitively you should assume that it's 1/2. Yes. So why? Because the number of sequences of length n having p 1/2 percentage of n, so ppn. So this is this number of combinations like here with n positions and pn ones. This number is typically Shannon entropy, 2 to the power size times Shannon entropy given by this formula. So for very large n, only the maximum Shannon entropy, which is 1/2, we can see in this plot, is essential. The rest asymptotically are the number grows much slower. So asymptotically we can. So assuming given P is a restriction to subset of possibilities with given percentage of ones, and asymptotically the ones maximizing entropy will dominate. So this is example of James' principle of maximal entropy, more general, but not knowing some parameters, statistical parameters like here, the safest assumption, if there is no reason to assume otherwise, is the maximizing entropy, because they describe the subset which grows the fastest, which asymptotically would dominate the many possibilities. Okay, let's look at the simplest case for maximal entropy random walk being somehow better than standard random walk. So imagine it's called Fibonacci coding, that we have sequence of zeros and ones, but after one there has to be used 0. So we cannot have used 2 neighboring ones. So looking at the graph of possibilities, so after 1 you have to go to 0, but after 0 you have some probability q of using 0 and 1 minus q of using 1. So the question is how should you choose this q? Yes, so naively you should choose 1/2. However, here is the plot, and turns out that 1/2 is not the maximum of this plot. You should use this a bit larger 0.61, this golden ratio q. So how it is found? So for given q, you can find a stationary probability distribution. Yeah, so how often we will visit given node, and then we can find mean average entropy. So this is entropy, Shannon entropy, averaged over stationary probability distribution of nodes. So how many bits per step we will on average produce during such very long asymptotic behavior? So why it is not maximized in 1/2 but 0.6 something? So intuitively using 1/2 would maximize the number of bits we produce in this one step. However, wanting to maximize the mean number, increasing this Q, we will more often be in state in which we will be able to produce information, because going to 1, we will have to jump to 0. So there will be no entropy from this one position. Okay, so finally we have this general situation that we have a graph M, and we would like to choose a stochastic matrix on this graph S using only the edges. This stochastic matrix determines some stationary probability distribution, and we'd like to find it such that so that the mean entropy reduction average of the stationary probability is as large as possible. So how to find it? So like in the previous slide, so while looking at the sequences, we shouldn't think about singular steps, but to maximize entropy, we should use ensemble uniform among entire sequences. Yeah. So the question is, assuming this infinite sequences ensemble, what is the percentage of zeros after zeros, and you will get this number. Okay, so here is some diagram. So in standard random walk, having three possibilities, the walker indeed throw a dice and makes the choice accordingly, maximizing entropy locally for each step separately, and for MERW instead it maximizes entropy globally, so averaged, and it leads to uniform probability distribution among paths. So each path infinite is equally probable, infinite path or finite one. So for each 2 points, each path between them is equally probable. Here is some situation for this lattice with defects. So we can see that after 10 steps, the squares mean that there is a removed self loop. So there is self loop usually, but in the square there is a removed self loop. So for after 10 steps, we can see the situation is similar. After 100 steps, it becomes different. Yes, and for 1000 steps, it's completely different. So from standard random walk, the probability distribution stationary is nearly uniform. While for MERW, it is strongly localized, as mentioned. So this is called Anderson localization. And in quantum mechanics, we also have exactly the same formulas. So, but they are two different philosophies. So in GRW, you assume that Walker indeed uses these probabilities. However, in MERW, we assume that it makes some complex dynamics, but we just don't know it. So only this is our model to predict best the behavior. So MERW has nice properties that it's kind of scale-free. That usually these discrete graphs come from some discretization of continuous situations. So usually to be dependent on the scale we choose for discretization. However, for MERW, it is scale-free in that. Because instead of random walk can be seen as uniform probability distribution among length 1 path. Then we can take GRW index 2, uniform probability distribution among length 2 paths, so 1 up and 2 down. Length 3, and each of them determine probability distribution for each single edge. And in the limit we will get MERW. Yeah, so this way is scale-free limit of GRW that we don't no longer think about single steps, but go to infinity these steps. So I will further derive this formula. Another view on this scale-free way is that having some matrix M and taking its power for MERW, it is just taking the power of the stochastic matrix. So it doesn't matter what discretization we choose. However, for GRW, it is usually not true. Also, the time symmetry for Maximal Entropy Random Walk is also much more natural. Just reverse the paths in ensemble. So let's look at the derivations, spread derivation. So we have an ensemble of paths starting here and now going to some position in this moment and ending here. So combinatorially, we have this formula, the number of paths. So m to power t and indexes yx is number of paths of length t starting in y and in x. So this is the number of paths before here. Then this is the number of paths after. And now we would like to make the limit to t to infinity. And and we have this Frobenius-Perron theorem for connected aperiodic graphs that this graph has singular dominant eigenvector. So aesthetically, this power will become just coordinates of this eigenvector. So one psi from one matrix, second psi from the second matrix. So again, we get this Born rule, the squares, because of time symmetry. Yes, so thinking about the end here, it would be first power, but having in the center, asking about probability distribution in the center, you get the square. Literally, to get given value, you have to get it randomly from past and future, or in Isaac model from left and right. Okay, so another we can get the stochastic propagator by using pairs of such positions. So, and this is the final value that the probability of going to y being in vertex x is this mxy divided by this dominant eigenvalue, and this multiplied by this division of two coordinates of dominant eigenvector. So here is for the uniform path distribution among paths. In Ising model, we can replace this m being zeros and ones with e2 minus beta times potential. This way, the paths we have probability exponent of minus beta times sum of potentials over the path, so energy of the path. So at the end of this Ising sequence, we would have the first power. In the center, we would have the second power as in this derivation. So as mentioned, it can be used also for Ising model. So it is called Markov field. And there is this nice Hammerstein-Clifford theorem that Markov fields are the same as Gibbs field. So in Markov field, the probability of this question mark under condition of all the remaining is just using the condition of the for green dots. Yeah, so we don't need to know all the blue regions. So this is local version of Markov field. Or again, wanting to have the conditional probability distribution of these question mark positions, we just need to know the green dot positions. Or we can use it for scanning, that we scan line by line, and again this probability of this question mark, it depends only on this value of these green dots on this line boundary. So how to find this conditional probability at the end? So we can take some stripes of length W here, and the probability, what is the probability? The question is, what is the probability of pairs of such stripes? And we can use this MERW formula. And then now we have to marginalize it, sum over these stars, and find the conditional probability distribution, and we get a very accurate model using approximation of final width, this W of this. So W times infinite lattice. So having this model, you can, for example, generate sequences of given very close to perfect. So instead of using Monte Carlo, or find the parameters. Okay, so here are the formulas. So in standard random walk, just the probability of transition is just 1 over the degree of given vertex. The formulas further are quite complicated usually. So the stationary probability is simpler for symmetric. For general, it's complicated. Probability of path is kind of asymmetric. For the powers, it's complicated. Well, for MERW, everything becomes much more simpler. But we need to find the dominant eigenvector, and we get the formulas. The probability of path is uniform, is the same for assuming uniform path ensemble, and this Boltzmann ensemble in this product of M's. And we have this scaling, being scale free. Also, we can reverse easily. Find the opposite random walk toward path kind of, and the entropy formula is also simpler. So we can say mathematically MERW becomes a bit simpler, but it needs this non-local finding this dominant eigenvector. So that's a bit difficult general question. Which one is the more natural for various situations? And I think it's a very difficult question. For example, for humans, I think this standard random walk is more appropriate. But for example, for particles like electrons, the MERW is much more appropriate. Okay, so let's look at the simple situation, one-dimensional lattice, that we have this lattice like here with self loops. However, some self loops are removed, and so what is this? Here is this dominant eigen equation. So m psi equals the previous position plus the next position plus the same position unless there is the defect. So multiplying by -1, we get this stationary Schrödinger equation where this energy is T minus lambda. So maximization of lambda, finding the dominant eigenvector, is correspond to minimization of energy for this discrete stationary Schrödinger equation. So again, lacking quantum mechanics, we need to minimize energy. Here are some stationary probability distribution for MERW. For standard random walk, for this lattice, it would be nearly uniform, just 2/3 proportion. And here we can see that it's million times. So probability of being here is million times larger than of being here. So it's much stronger localization. And there's some like huge derivation of continuous limit and in potential, and we get this standard Schrödinger equation. We can get if using proper constants. And what about the excited states? Turns out they are also there, but different. So in standard quantum mechanics, having a single excited atom in theory is stable. To make it de-excite, it needs to interact with the environment. In MERW instead, it would collapse to the ground state, exponentially weakening the excited coordinates. So we can see that this, after 100 steps, it is closer to this excited state, and then finally it goes to the ground state. So because it started close to the excited state, then it first finds close excited states, then finally de-excite the ground state. Yes. Okay, let's now go to this p-n junction. So for serious model of conductance, it is more difficult because we don't have single electron, but we have also this cloud of the remaining electrons. So the question is how to handle them. So we can use this mean field approximation, that we can assume that the remaining electrons will have the same stationary probability distribution as this single Walker. But it complicates mathematically this problem. So here, generally, we need to find left and right eigenvector of this adjacency matrix, and here is the stationary probability distribution. However, now we need to find what is probability distribution of electrons, how it contributes to the potential. So we need to add this Poisson equation, which finds this contribution, and it go back, it modifies this M matrix here. So we see that it's more complicated to find it, and it's not that so simple numerically to solve, to make it self-consistent. But here are some examples. So we have these red dots as the positive potential. So these are atoms of the repulsion. So we have silicon lattice with some dopants, and some of them are positive potential, some of them have negative potential. So here is for positive, there are repulsive, and so here is without. So here is just a single Walker. And now we increase this gamma here, yeah. So we increase the interaction between this electron cloud. So we can see that the stronger this interaction, the more uniform the distribution of electrons. Yeah. So they push each other to make it as uniform as possible. Yes. So this is very difficult, very important, but also difficult to include term. Here are for positive, again, for increasing this certain interaction. It goes to uniform distribution. Okay, so to get this, to solve this Poisson equation, so to find potential contribution for electron density, it is calculated there is a variable GitHub source. So it is calculated in discrete situation. So we have Laplacian. For a cyclic situation, we can use cyclic boundary conditions. Up down this semiconductor p-n junction. However, left right there is a change of voltage. Yeah, so if using cyclic boundary conditions, it will have the same voltage, but there should be difference of voltage, which makes the electron flow. So instead, I have used reflective boundary conditions. So I'm saying that kind of electron going left from the left side bounces back and goes here. So here's the Laplacian used, and here is this solution. So inverted Laplacian for given position. So how electron in given node, what potential it produces. And here are some solutions on the right. So here is this situation, the density and the flows without this external potential, and here is with this forward bias, it is forward bias, it is backward bias. So here you can see there is flow, and here there is no flow. Yeah, so as in diode, in one direction electrons easily flow, in the other it's more difficult. So here is the found numerically Ohm law here, and we can see that so in one direction is linear. However, in the remaining, in the opposite direction, there is no conductance, and then there is breakdown voltage when conductance starts. And here are more simulations. So again, so here is without potential, and here is growing this potential in one direction. So we can see that the flow continuously grow. However, in this opposite direction, you see there is nearly no flow. However, there is breakdown voltage, and now the electrons start to flow very, very quickly. Also, there is some interesting shift of some boundary with change of the potential, so which might be worth analyzing. So these kind of models are relatively cheap to calculate in comparison to full quantum conductance model. However, they are missing. They have the same stationary probability distribution of quantum model. However, they are missing interference. So there is no interference here. So the question is, if given situation, interference is crucial. Maybe it would be interesting to compare such predictions with full quantum, and the difference should be just the interference contribution. Here are some formulas, but maybe let us skip. And let's go to the next article from this January. So now we would like, so standard maximal entropy random walk. Let's use this nasty paths. Yeah, so it's ensemble like in Brownian motion. These are these paths which are nowhere differentiable, and the velocity goes to infinity in this infinitesimal limit. So these are not really physical intuitively trajectories. So could we use ensemble of more smooth trajectories? And yes, from one side it can be done. So it can be done by going to phase space. So instead of random walk just position, we have a change of. So now we have position and velocity. The velocity deterministically determines the change of position, and now the velocity changes randomly, like let's say plus minus 1. Yes, so we have diffusion in velocities which determine change of position. So like the Langevin situation, however, now it's done in this MERW philosophy. So ensemble of paths which become the smooth paths. So looking at the equations of standard MERW, we got this Schrödinger equation. However, in PS MERW, so this Laplacian standard came from this plus minus 1 in position. So we get this spatial Laplacian. However, here we have this plus minus 1 in velocity. So now this Laplacian is over velocities. And in the article there is more strict derivation. And also this change of position with velocity now corresponds to this term with gradient. And there is plus potential in space plus this kinetic energy. And so we get this kind of phase space Schrödinger equation. So it turns out I'm not the first who has found it. Also, Jean-Pierre Bouchard in 2017 earlier for Schrödinger equation for Feynman path ensemble. But generally there is a big question that we use this in quantum mechanics, this Feynman path ensemble. So the naive ones use these nasty trajectories which are not very physical. So the question is, should we use this nasty or maybe more physical paths in this ensemble? So I think this is more than just a philosophical question, because they lead to different stationary probabilities, for example, to different behavior. So here is some random trajectory example for the standard diffusion in this 0, 1 with a uniform stationary probability distribution. Here is for MERW with sine square and quantum mechanics stationary probability distribution. And here is for PS MERW. So it turns out that it's a bit different. So it's kind of close, not exactly sine-like stationary probability distribution. So different boundary behavior. So intuitively, where this difference comes from? So because here we have this velocity, the walker can randomly gain velocity, and what makes it easier for it to get close to this barrier. Yeah. So that's the intuition for the difference with the far farthest in tunneling. So the big question is which are the appropriate for various situations. So it would be great to have some experiment which is able to distinguish these two types of stationary probability distributions and determine which one is more appropriate for given situation. So the difference might be quite subtle. So for example, for Gaussians, for harmonic potential, they are very similar. So the correction might be really tiny in practical situations. So here are some situations, yes, for this harmonic potential in Gaussian. So we can see that the deformation is very small. So the green is using this phase space random walk. Here is from this infinite potential, well, like previously. And here is from this Coulomb or Newton potential. So for example, for the dust around the planet, for example. So random walk would say that the dust should have nearly uniform probability distribution aesthetically. What makes little sense, so it should rather have this MERW like have exponential finally decline. So they first find the probability the psi in so this amplitude in phase space. So here is position, here is velocity, and then we need to multiply to getting the stationary probability distribution finally. Okay, so now let's go to the tunneling. So there are these very nice Boltzmann droplet experiments I have mentioned. That they have this vibrating surface, and there is Boltzmann droplet. And I've mentioned that they get this wave-like statistic for the trajectory. And now another article they show tunneling that they have a barrier, and the probability of crossing this barrier drops exponentially with its width. So here is this plot, the experiment. But also from the velocity. If you have a faster walker, it is easier to pierce a barrier. Yeah. So also aesthetically for very high initial velocity, it should be easy to pierce the barrier. So here the philosophy is that there is this coupled wave that the walker has also creates these waves, and this gives it some history, the complex dependent on its history. So if it is nearly random, then the probability of crossing a barrier becomes dependent on this noise-like field, making it practically random. Okay, so now let's look at tunneling for the mentioned methods. Here is some example that we have some finite barrier in one dimension plus velocity, and here is some probability distribution evolution. So for standard random maximal entropy random walk, and for this phase space PS as phase space random walk. So we can see that there are some slight differences. So again the boundary behavior is quite different. So this first power versus second power, because of this randomly gaining velocity to get close to the barrier. And also here is some example trajectories. We can again see there is large difference. So in standard MERW and quantum mechanics, it would be kind of the diffusion to the barrier. Instead, in this phase space MERW, again the walker randomly gains velocity, what makes it easier to pierce to the barrier. Yeah. So the question is tunneling related diffusion or maybe piercing by randomly gaining velocity? There's also a very nice deterministic model using this history dependence in this arXiv, you can see. And here is this tunneling probability calculated for this PS MERW. So here is the setting. So we start in this green line, start, and the question is, what is the probability of getting to the finish, the blue region, avoiding this pink region. So it is the walker is absorbed in getting there. So these widths at the ends are constant. Only we change this barrier width. So the entire setting changes the width. So looking at the probability of tunneling versus the barrier width, you can see that in log plot, asymptotically, it's nearly exponential drop with the barrier width. Yes, as it should be. Also looking at this probability of tunneling versus initial velocity. For very, very high velocity, we can see it's easier to tunnel, finally approaching 1 for very high velocities. We can also focus on a single situation, which is for this widest barrier, and look at what is the probability of the number of steps. Yes, so how many steps it requires. So you can see these are finite velocities. So somebody claimed faster than line tunneling, while here you have only lower velocities. So basically, if we start with a low velocity, it has to be randomly increased to make the tunneling what has low probability. If you start with high velocity, the mean velocity will likely be reduced, but the tunneling probability is high. And let's finish slowly. So as mentioned a few times, there are these squares both in Maximal Entropy Random Walk and quantum mechanics due to the symmetry that in given moment paths ensemble toward past and toward future meet, and the probability that both we give given value is the product of two probabilities, getting the squares. And having the squares, let's see that we can violate Bell-like inequality. So let's take a look at this diagram. So there is this inequality which is simpler than Bell's. It's called MERW's inequality, that tossing two coins, at least two give the same. It's completely obvious. So let's derive it using this formula. So let's derive this inequality as this formula. So probability that A and ABC are the three coins, the binary variables. So probability that A equals B. You're looking at the joint probability distribution. So we have 8 possibilities for three coins. So A equals B are these four situations for values of A and B's. So A equals C are these 4 situations, B equals C are these 4 situations. So if you sum all three, you get this matrix having at least 1 in every position. So whatever joint probability distribution among these 8 possibilities we choose, this will be at least 1, yes, because we sum also we get at least this 1 normalization of the probability distribution. So it's kind of obvious. So it has used this Kolmogorov axiom that probability of alternative. If you don't know this question mark, we should sum two probabilities. Yes. However, in quantum mechanics, we can replace this third axiom with the Born rule, which has the proportional to sum of amplitude squares. Yeah. So because of this symmetry, so we have one question and 2 answers. So let's look having these squares. It is natural that we can violate inequalities. So we derive inequalities assuming one formula, this third axiom. So it is not a surprise that changing this formula to Born rule, we might be able to violate the inequality. So here is the amplitude which has the strongest violation. So these 2 zeros for up. So so having the same values, and using it, we get 0.6. So we get violation of this MERW inequality, and it can be realized in Ising sequence. So we have sequence of 3 spins with interaction enforcing this amplitude. So there are forbidden 3 spin up, 3 spin down, and now in given position we measure 2 out of 3 spins. We cannot measure all 3. If we measure all 3, then we get again this Kolmogorov axiom. The inequality has to be satisfied. So it's crucial that we measure only 2 out of 3 spins, and the probability. So looking at the probability at the end of sequences like here and here, it would be the first power like this psi, but also here and here. So now we have to multiply them for the Born rule, and doing so we get the violation of inequality already in this Ising model, which mathematically is very similar to quantum mechanics, replacing Feynman path ensemble with Boltzmann path ensembles. And here is the last slide. So I have tried to convince you that we need time symmetry for the Born rule, for quantum mechanics, for Bell evaluation. And so then we have these two philosophy of time. We naturally use this presentis, that we have some present situation it evolves. However, physics in many situations, for example, in general relativity, if Feynman ensembles, Feynman diagrams, require to use these eternalis that we have the time symmetric situation. And we have this, so we have the least action principle and classical mechanics, which corresponds to either Ragans in this picture, or Boltzmann ensemble. Here it is MERW diffusion, or Feynman ensemble, Feynman diagram ensemble in quantitative QFT, which corresponds to Schrödinger equation and allows to validate the line inequalities. Thank you.